Okay, good afternoon. Can you guys hear me? Okay, good. So, today, okay, I will just present what I have at the moment. So, we are supposed to start with this lecture, but I will go back to the previous lecture where I promised to justify some calculations. I will replace the notes for lecture 11 sometime later. Okay, on the Putra Blast. So where was the problem previously was, yeah, I think it was here. Okay. So recall that we had these two equations. So these two equations we get from looking at this Schrodinger equation in the degenerate space. Oh, sorry. Right. Sorry about that. Okay. Let me go back to what I mentioned just now. So before we go to lecture 12, which I've only partially finished the notes, let me go back to lecture 11 where we had this Schrodinger equation perturbed by this potential here. And what we did was to project this into two subspaces, one which is in the degenerate subspace, and then the other is essentially P1 is essentially the space of states which is not the degenerate subspace. Okay, and we can project this equation to two individual equations for the respective subspaces in this way. So we have done that. I think there's no problem with that. But then it comes to here where we need to show that. Okay. So let me just go to the whiteboard instead, so that I can do this step by step. So essentially we had this equation, I think this is the second equation, lambda P1 V P naught, oops, some delay here. Okay, some problems. Okay, lambda P1 V P naught L plus E minus H naught minus lambda P1V P1L equals 0. So this is the perturbed state. Okay. So what we can actually do now is to rearrange this equation. So I'll just do it step by step here. E minus H naught minus lambda P1V P1L equals to lambda P1 VP naught L. And here one can think of sort of bringing this whole operator to the other side. So just bear with me. This seems so cool. There's a problem of definition of the operators here, but let's say we can do this. E minus H naught minus lambda P1 V P1, and then you have your lambda P1 V P naught. Okay, so I'm going to multiply this by P1. Reason why I want to do, I could have actually leave P1 there, but I want that form. Okay, so that's why I'm doing it this way. So times by P1, so that actually gives you P1L equals to P1. Being careful here, or maybe I should write the lambda. Lambda is just a parameter. Lambda, so I can bring this up to the numerator. E minus H naught minus lambda P1 V P1, and then P1 V P naught. Now, one of the things with projection operators, you can sometimes just simply make a projection because that's no. Let me just see this in the first place. Okay, maybe this will be better. This lives in this equation lives in P1 subspace. So I can always add this operator P1 anywhere, so that because essentially just to ensure that if there's any, for example, this V, for example, could have actually bring the vector outside the P1 subspace. So one can actually multiply P1 anywhere inside this equation, okay, to ensure that it's still inside this P1 subspace. So let me see what else. Okay. So one of the things over here is you see that this P1 is outside the bracket, okay, but over here, this is just an eigenvalue, your perturbed energy level, and then your H naught commutes with P1, okay. So I could essentially ignore the multiplication of P1 because the whole thing is going to be projected by P1 over here. So I can now say that this can be given as follows: E minus H naught minus lambda P1 V P1 and P1 V P naught. Okay, so this brings almost to the same equation that we had in the notes and the book. So let me push this thing up. So once you have that, then you remember that I'm going to put this L in terms of power series and lambda. So let me just write that down. P1, and then this is L naught plus lambda L1, the first order correction, and then higher orders. And the same thing for the other side. P1 lambda E minus H naught minus lambda P1V P1 P1V P naught, and then the same thing, the expansion here. And now we start to take the linear term in lambda. Oops, I don't want to do that. Oops. Come on, my cursor is. Yeah, I suppose that's good enough. So take linear terms in lambda. So that means this and that. Yeah, so that gives you P1 L1 equals to, over here there's already a lambda here, so in other words we can only multiply with that. So that gives you P1, yeah, yeah, again we'll do the trick in a minute. P1 1 E minus H naught minus lambda P1 V P1 P1 V P naught L naught. Now I can remove this P1 because no, I already have P1 over here, and also for this part there's already P1 inside this terms, so that sort of guarantees you to be always inside the space. And that simplifies to this. So you can see some of the assumptions taking place inside this expansion. And okay, let me just write down that thing first. And now you use the fact that psi over here, P1 is essentially sum over K not inside your degenerate subspace of K naught, K naught. Okay? So I can now substitute that inside over here. That gives us this. P1V, P1, sum K is not in D of K naught V, sorry, we're doing K naught, K naught, V, P naught, L naught. Okay. But L naught is already in the degenerate subspace, so I can remove the P naught there. So let me just remove that. Okay, so that becomes L naught. Okay, because P naught L naught is just L naught. L naught is in the degenerate subspace. So now what we have here is already the matrix element. The only thing that we need to worry is the denominator here. So we need another fact that essentially I've forgotten in the last lecture is that recall that your perturbed Hamiltonian is given by something like this. Yeah, H naught plus lambda v. Okay, but now what I can try to do is to write this into two parts of this interaction terms, the two parts by having the projection this way. Okay, so this gives you the interacting potential in the degenerate subspace, and this will be interaction in the other subspace, which is not the degenerate subspace. So how is this going to be used is to see that your E here is your perturbed eigenvalue. Okay, and if you look at that, you see it takes away this part. Okay, so in other words, what's left is going to be this part, really. So this part is the interaction inside the diagonal degenerate subspace. So your E minus H naught lambda P1 V P1 will give you essentially your ED naught. Okay. No, sorry, not that one. E minus lambda P1 V P1 will give you ED naught. So that gives us that term. Go back here. The confusion was the one at the denominator here. So essentially, that leaves to this particular denominator. Okay. So I think the rest you can figure out yourself because they are pretty straightforward. But the one here probably needs a little bit of what you call long-winded kind of arguments. Okay. Right. So this is I've added few more explanations inside the notes. I will replace the ones in the Putrablast. Right. So the next thing that we want to do for today is essentially to talk about some more applications of your perturbation theory. Okay. And the first thing that we want to actually see is the case of relativistic corrections. Okay. So if you look at the Hamiltonian that we have for the case of a hydrogen atom, for instance, essentially we have your kinetic energy here and then your Coulomb potential. Okay. So one of the things that probably of concern over here is whether this term that tells about the kinetic energy of the electron orbiting around the nucleus, okay, whether that is near the speed of light or not. Because if it is, then one should be using, instead of the non-relativistic, this is non-relativistic kinetic energy. Okay. So instead of doing this to be non-relativistic, then you have to take into consideration the relativistic effect. And if you look at the speed of electron in the ground state, okay, you can make estimate that your speed of the electron is about alpha times c. C is speed of light, speed of light. Speed of light. Okay. And alpha is essentially a constant that we should learn later on called the fine structure constant, okay, which is 1 over 137. Okay. So in other words, this is already quite close to the speed of light. So in other words, what one needs to do is to replace the kinetic energy term over here by the relativistic expression. So we have, I think both of you have done special relativity. So you know that this is the relativistic kinetic energy, which is your P squared C squared plus M squared C to the fourth square root minus the rest mass energy. Okay. And now this is a bit complicated for us to use inside this Hamiltonian. So what we do, we Taylor expand this. Okay, you Taylor expand this, then you get back to your non-relativistic kinetic energy here. But there are corrections. Okay, so what one can do in this particular case is to consider the corrections is just like another potential. Okay, so this will now be considered as your perturbing Hamiltonian, in which case the original Hamiltonian is just the ordinary one. Okay, and this one you know what the energy states are, which is just your NLM. So the other thing that one needs to worry about is, okay, what kind of perturbation theory that one should use. And you know, for example, besides the ground state where n equals to 1, okay, your NLM is essentially very highly degenerate. Okay, so this can be a horrible thing to do, but we try to make use another fact that simplifies this, is that your angular momentum operator commutes with p squared. Okay, essentially, if you remember, your L commutes with h. Okay, so your L commutes with p squared. Then from okay, how should I say? You can this one you can actually prove it directly. So the only thing that we need to worry inside this Hamiltonian, okay, is whether the potential is commutes with the angular momentum. But the potential, you remember, has ER, which doesn't depend on any particular direction apart from the radius between the nucleus and the electron. So in that particular case, then you also have L and V to be what am I saying? No, okay, I've forgotten about this. This is H naught. This is the thing I wanted to say. The V over here is your perturbing potential. Okay, so here is the perturbing. So I'm getting all the logic mixed up. And because of L is actually commutes with your H naught. That means L commutes with P squared because your Coulombic potential is also independent of direction over here. So L commutes with P squared. So that will tell us L will commute with this P squared over here. Okay. So what does that imply? That also implies that this thing is already rotational symmetric. Okay. So V is rotational symmetric. So if you get the matrix element of that V, so maybe I should differentiate this, say V naught over here. Okay. Then you expect this will not be dependent on this m, what you call m value. Okay. So in other words, what we have is that this will be already diagonal because it doesn't depend on the directions, and that tells us we can apply straight the formula for the say the perturbation theory that we had earlier. We can apply straight to this perturbing potential directly. Okay, and you can see that okay in this particular case, the index being written here is only n and l, but it doesn't depend on m. Okay, so that tells us okay we already know that this is supposed to be diagonal. Okay, so the only thing to do now is to find out what this expectation value of this quantity here. Okay, one could do this in a way we have done expectation values, but here you have to remember this is probably involve so this is p to the fourth, that means you involve derivatives, the fourth order derivatives. You wouldn't want to do that. Okay, so it's much simpler to find another technique. Okay, so another technique is to consider the following. Your p squared already appears in h naught, right? So what can one do is to remember what h naught is. H naught is p squared on 2m plus, sorry, not a plus, oops, never mind. P squared on 2m minus z e squared on r. So then we actually have h naught plus z e squared on r equals to p squared on 2m. Okay, which is a thing that we have over here. So in other words, you actually square this thing. Okay, squaring this thing will be much simpler than evaluating this term over here. Okay, so what do we have in this particular case? So for your h naught, we can evaluate directly because h naught is the unperturbed Hamiltonian acting on the unperturbed state. So that will just give you en naught square. Here I miss out e naught again. I'm trying to type this in a rush. This is coming from the cross term inside this square. So you have your h naught multiplying z e squared on r. Okay, so you have en naught there, and then the expectation value of z e squared on r, and then the other square value is this one. Okay, so all we need to do is now to have the evaluation of this term and also this term. Okay, now one can again do this directly. one should be able to do this because there is a formula for expectation value of 1 over r. I can't remember what it is, but you can check your first course. Okay. And then m here, one can find what this is. Okay. So in other words, you can actually evaluate this directly, and the same thing over here. Okay. There is another formula for 1 over r squared. So in principle, you can actually already do the calculations over here to find the first order shear. But if you want to be fancy, one can do another way of doing it is to consider your H naught here, okay, and then you perturb it with another, sorry, not lambda here, confused, plus, so here I'm just saying that this is going to be our additional term, gamma over r, okay. And what happens over here, if we do perturb this H naught with gamma over r, then you'll find that you're going to get the expectation value of gamma over r. Okay. So using perturbation theory. And then finally, when you get the answer of this, you replace back, forgotten. When you do this, for example, you can see that this is like replacing your ZE squared with ZE squared minus gamma. Okay. So then over here, you can evaluate this directly if you want to, or you can use perturbation theory. Okay. If you use perturbation theory, finally, you set back gamma to be ZE squared. So in other words, it goes back to the case of the no perturbation case. Okay. I've not shown this over here because this is supposed to be part of your assignment for perturbation theory. So, but the idea is just simply that, okay? And you can actually also do it directly using that formula. You can find it somewhere. And then you find that this expectation value of ZE squared on L, so ZE squared on R is equals to minus 2 EM naught. Okay. So the next one is the third term over here. The third term, again, we can use perturbation theory if you want. Okay. Or you can use direct integration. With perturbation theory, you sort of write your H to be H naught plus gamma on R squared. Okay. Different from the one above. Okay. So here is really acting like a potential that you need to calculate what it is. But you also know that in the case of the H naught, you have done solutions to the hydrogen atom, there is a term coming from the angular momentum operator, which is in this form, and this is called the centrifugal barrier. What it does is essentially to prevent the electron to move too near to the nucleus, because this will get large. Okay, so that's essentially the centrifugal barrier. So in other words, this gamma on R squared sort of perturb this centrifugal barrier. Again, one can do the perturbation theory if you want to, but let me just leave that as an exercise. So that's why I'm saying today's lecture will be short. You can actually prove that For the third term, it's going to be giving you this particular value, which you can see that this is the linear term in terms of your energy here. This is a quadratic term in terms of energy, which makes sense. Okay. So one can now plug those back in. So you can see that your En naught squared is here. En naught times En naught again is a square. And from here, you again have the En naught square. So really, if you know what En naught is given in terms of this. For the hydrogen atom, it's actually given nicely in terms of this. Z equals to 1 for hydrogen atom. You get 13.6 eV on N squared, which things you already know. Or you can re-express it in, much more generally in terms of your structure constant alpha there. Okay, so you can plug those in, and finally you get this correction, the first order shift. Okay, so that is where my notes is done. Okay, so the next thing that we should be doing is to talk about spin orbit interaction, and then here essentially where you get the fine structure constant really comes into play. So I think I will stop that for today. Is that okay? So because I've not finished, yeah, I've not finished my notes. So by the way, how about your assignment? When can you hand it in?
Doctor, could we ask you something earlier? Yeah. Could we postpone test two?
When do you want to have it?
It's either Friday maybe or the week after, the Monday.
What week is that?
Oh.
Okay, we can push it to week 13 because there's only 3 of you.
I think we all have the very similar schedules.
Okay.
Yeah, because next week is submission of FY2 draft, so we'll be quite busy over the weekend.
Yeah, I also have my seminar in Istanbul for me to prepare. So I'll be pretty busy. Okay, for Friday, for example, I will not be able to do the FYP meeting. So for you, Joshua. Okay, and I have this call this latihan industry thing for me to settle. Okay, so okay, let me take the attendance list.
Postponing test two to week 13, right?
Yeah. Monday, yeah.
All right, okay, doctor. So submission of assignment two, I assume will be postponed as well. Sometime next week, maybe.
Sometime next week, when precisely?
That is the question.
Sometime.
Yeah, I think that'll be all right.
Okay.
Midweek?
Oh, no, I mean, okay, I'll let you decide.
We'll talk about it, doctor.
Okay, right. I think that's it for today. All right. Anything else you want to?
Doctor, just a short thing.
The draft.
Can I email you my FFP draft?
Yeah, I got your earlier draft. So I have not, I was so busy doing other things, so I have not seen it. When it precisely you want me to? When do they want it?
They want us to present it on week 13. So week 12 is actually where we'll do any corrections from our supervisor's reports.
So you want me to give you next week then?
Possible.
Okay, certainly I'll be busy from now until Saturday because Saturday is my talk. So maybe after the talk, I can, I have a bit more time to look at things. Okay. So I can. Okay.
The rest, if I'm done, I'll send you my intro and theory if I'm done over the weekend.
Okay.
So yeah.
All right. Okay.
All right. Thank you so much, Doctor.
Okay. Bye.
Good luck for your talk.
All right. Bye.